Pour particles of sulfur into water and they sink. Pour them into carbon disulfide and they dissolve. Grind them up small enough and disperse them in water, and they will do neither. They will remain in suspension. Millions of gallons of water suspended in the sky. Clouds are colloids. Tons of solid matter suspended in the air. Smoke is a colloid. A colloid can be a solid suspended in a gas. It can be a gas suspended in a solid. Milk is a liquid in a liquid. Stained glass is a solid in a solid. The jellyfish is a liquid in a solid, or a colloid can be a solid in a liquid. Whatever the colloid, it must have two parts. The particle, for convenience here in the form of a carbon paste, and the medium in which it is suspended. The particles are known as the disperse phase, and the medium as the continuous phase. The colloidal state may not always be apparent to the eye, but particles scatter light, shine a beam through the medium, and you will see they are there. This is called the Tyndall effect. Why do some particles remain in suspension? Matter, if it's denser than its surroundings, will tend to sink. Why doesn't this happen in a colloid? In the medium, the continuous phase, the molecules are in rapid random motion, constantly colliding with the particles. If the particles are small enough, these collisions keep them moving and thus stop them sinking. This movement is called Brownian motion. Brownian motion can be observed under a microscope with particles between about 10 and 10,000 angstrom units. That is, between 1/10 of a millionth and 100 millionths of a centimetre. With larger particles, gravity becomes dominant, while smaller particles dissolve. However, other factors are involved. There are forces of repulsion and forces of attraction. Matter itself is mutually attractive, and particles, if they collide, will tend to stick together. These forces of attraction are known as van der Waals forces. If the suspension of particles is dilute, the chance of collision between the particles is small and the colloid remains stable. But if the suspension is more concentrated, the chance of collision is greater. The particles will tend to coagulate and they will sink under gravity. So in a concentrated suspension, other forces must be present or the colloid will not remain stable. There are in fact two kinds of colloidal systems. The particles in both are electrically charged, though in one system the charge is the dominant factor. This system is the more universal. A cloud is a colloid in which electrical forces are dominant. In a colloidal system of this kind, the particles all carry like electrical charges. Since like charges repel, the particles cannot approach closely enough for van der Waals forces of attraction to be effective. The presence of electrical forces in a colloid can be shown by the movement of particles in an applied electric field. Reverse the field, and the movement too is reversed. This movement is called electrophoresis. By mixing solutions of silver nitrate and potassium iodide, a typical colloid in which electrical forces are dominant can be made, colloidal silver iodide. The type of charge on the particles will depend on whether the negative iodide ions or the positive silver ions are in excess. In either case, the existence of the colloid can be seen from the Tyndall effect. Systems in which the particles must be electrically charged to form a stable colloid are known as lyophobic. In such colloids, stability increases as the particle size increases, because the larger the particle, the more ions it will absorb, and consequently, the greater will be its electrical charge. Such colloids are known as lyophobic sols and are usually solids dispersed in a liquid or gas. A jelly is an example of the second kind of colloidal system, where electrical charges are no longer the dominant factor. For this, the medium must be a liquid. Here, stability depends on an affinity between the particles and the medium, allowing the molecules of the medium to attach themselves to the particles. This forms a coating which prevents them coalescing under van der Waals forces of attraction. In contrast to the first type of system, the lyophobic colloids, in this case, the smaller the particle, the more stable the colloid. Take the surface of a cube. The same volume divided into 64 smaller cubes provides a surface area 4 times greater. So, the smaller the particle, the more molecules can be picked up, and the more effective the molecular barrier will be. Particles which have a strong affinity for the continuous phase are known as lyophilic. In concentration, some lyophilic colloids tend to be viscous. They may even acquire some of the properties of a solid and are then known as gels. This happens when the particles are long and thread-like. They link with each other through the molecules on their surfaces, and these linkages can extend to form a network throughout the mass. This process is reversed when heat agitates the particles so that the linkages begin to break. The gel eventually liquefies, but on cooling, the linkages reform and the colloid gels again. Thixotropic or jelly paint is a practical application of a reversible colloidal gel. though in this case it is mechanical action rather than heat which breaks down the linkages and allows the gel to become liquid. But all gels are not reversible. Some thread-like particles can form long parallel chains which are irreversible when the chains are cross-linked. Cotton and silk are examples, and we use the same principle in making nylon or terylene. The white of a fried egg is another irreversible gel. Sometimes a lyophobic colloid may be made lyophilic. Take a lyophobic gold sol and add an electrolyte. This overcomes the charge on the particles and the dispersion changes color, showing that the particles are now coagulating. But what happens if a protein solution is added first? The gold particles will be coated with a protein barrier which has a strong affinity for the continuous phase, and this barrier, therefore, becomes coated with molecules of the continuous phase itself. Now, when an electrolyte is added, the loss of charge is no longer of significance, and no physical change is seen, because the particles have remained in suspension. The colloid has become lyophilic. Milk is a common example in which lyophobic particles of liquid fat are surrounded by protein which keeps them dispersed as a lyophilic colloid. The effect on oil or grease of detergent action is another example. It is basically a lyophobic material being suspended as a lyophilic colloid. Detergent molecules consist of a water-loving or hydrophilic head attached to a water-hating or hydrophobic tail. The hydrophobic tail is repelled by the water and attaches itself to the surface of the oil. Stirring the oil breaks it into droplets, which, because of their detergent coating, cannot then coagulate. Detergency is one of the many ways man can usefully apply colloidal principles. Colloids can be natural or man-made. But whatever it is, a colloid consists of two parts or phases: a disperse phase and a continuous phase. Colloidal particles must be small enough for Brownian motion to counteract the force of gravity, but not small enough to go into solution. Particles tend to be drawn together by van der Waals forces of attraction, and where these forces predominate, the particles coalesce and sink. Two kinds of forces can prevent this. The first is one of repulsion between particles carrying like charges. The larger the particle within the colloidal size range, the stronger the force and the more stable the colloid. Particles such as smoke, which are prevented from coalescing by the repulsion of like charges, form lyophobic colloids known as sols. The second force is one of attraction between the particles and the molecules of the continuous phase. In this case, the smaller the particle, the more molecules are picked up, the stronger the force, and the more stable the colloid. Particles with an affinity for the continuous phase form lyophilic colloids known as gels. We are surrounded by colloidal systems. The colors of this film are colloidal. Even the film itself is a colloid.